Hi everyone, my name is Jack, and I work at Alibaba, mainly focus on the Flink SQL and the table API. I'm also a PMC member and committer of Apache Flink. Today, I want to share with you some internals of Flink SQL. So here is the agenda. During the last two major versions, 1.9 and 1.10, Apache Flink community spent a lot of effort to improve the architecture for further unified batch and streaming processing. One example is that Flink SQL added the ability to support both old planner and the new Flink planner under the same API. We will first discuss the motivation behind this movement, and then we will deep dive into how Flink SQL works, and also share some major improvements in the new Flink planner. So before I start, I really want to say that all I will present now is a joint work of the entire Apache Flink community. So thanks to the whole community. So a little background. This is the Flink original architecture. Flink can be deployed in various environments, such as a single JVM or a standalone cluster, or YARN or Kbers. Flink has a unified distribution streaming runtime, and based on that, we have two dedicated API. One is for streaming, and the other is for batch processing. The table API and SQL is actually built on top of them, and it will translate queries into these two API depending on it is a streaming query or a batch query. As you can see in the picture, this doesn't really look like a unified architecture. And we can take a step closer to see the underlying of this data stream and dataset API. In a short walk, they are not unified, and we have too much duplications. Every time if we want to add some features, we have to modify the whole stack for both the data stream stack and the dataset stack. The code is hard to reuse because we have different APIs, and the translation path is also different. Dataset has a small optimizer in it, which often conflicts with our SQL scope optimizations. This makes us very upset, and besides, the execution mode is also different. We have a push-based operator in streaming, but we have a pull-based driver for batch. So you have to think different and write different code for them. After some research and POC, we started to figure out that the streaming side is the only thing we need, and we can unify the architecture into this part. So this could be an architecture for future. Every level is unified in its whole stack. And we have a unified API, we have a unified planner who can do both batch and streaming, and we will translate the query into a unified DAG, which consists of streaming transformations and operators. But we still need to do it step by step without breaking any compatibility. We still need to support the old planner because we would like to give users a smooth upgrading experience. So actually, the community came up with a very nice solution. We introduced a pluggable planner architecture. We can keep all the old logic in the Flink planner, and we can try everything new in another new planner. We call it a Flink planner because it is contributed by Apache Flink project. Users can easily choose the planner to use with a single line of configuration. And the Flink planner is the default planner in 1.10 and 1.9, but in the upcoming 1.11, Flink planner will be the default because which also means it is ready for production. And I will present today is all based on the latest Flink planner. So this is the motivation behind why we introduced Flink planner and why does the architecture looks like this now. Okay, let's take a look at how Flink SQL works. This is a high-level overview of how Flink SQL works. Flink SQL supports SQL and the Table API as the public relational API. Table API also supports Java, Scala, and Python languages. Flink has an internal representation of a user program called logical plan. We will convert the public API into those logical plans. The conversion will involve catalog. A catalog will help to look up some metadata information to resolve the functions and resolve the table paths. It can be a Hive metastore or a user-defined catalogs. A logic plan is a start point of the optimization. So it represents a logical computation on a dataset without worrying about the execution details. Once we have the initial logical plan, through a lot of different optimization rules, the Flink SQL optimizer will convert the initial logical plan into an optimized physical plan. And finally, through the Flink SQL code generation, the physical plan will be translated to a DAG of transformations. The transformation is an internal stream API under the data stream. In this layer, we also have lots of optimizations. We have improved the code generation to operate on binary data, and we have state-of-art operators. We have fine-grained resource optimizations. At last, the transformations will be converted into job graph, which is ready to be executed. The job graph can be submitted to a Flink cluster for distributed execution. So workflow path before the physical plan is unified for batch and streaming, including the optimization rules. But we will have different physical plans and transformations for batch and streaming because they have different runtime behavior. And I will give an example to explain the workflow. In the left side, it is a simple join query which joins T1 and T2 with a condition. And in the right hand, it is a passed initial logic plan. So you can see that the T1 and T2 is passed into scan nodes, and the join operation is passed into join node, and the where clause is passed into the filter, and the select clause is passed into the project node. And they all represent a specific data operation, describe how to generate a new dataset from the input datasets. And a logical plan will then be sent into the optimizer for optimizations. And I will introduce some of the optimization rules. The first one is expression reduce. Expression is used to describe how to generate a new column using the input columns. In this example, we can find 4 kinds of expressions. Like for example, the 1 plus 2 plus T1 dot value. This is an expression. In Flink SQL, field reference and lateral values are also expressions. So as you can see, expression is a tree structure. And in the right figure, we have an expression tree which represents the 1.1 plus 2 plus T1 dot value. And by applying an expression reduce rule, we can evaluate the constant expression during the optimization phase. And we can evaluate the 1 plus 2 into 3 and convert the left tree into another kind of tree, and which is just 3 plus T1 dot value. And these two trees are equal because they produce the same kind of result. So this is a simple optimization to remove the 1 plus 2 for every row during runtime. And the second optimization rule is the pushing down filter through the join node. Still the previous example, we are joining two tables, T1 and T2, and then we have a filter to filter out the join result. And finally, we'll project the T1.id and 3 plus T1.value. So first look at this logic plan, we will find that T2.id is only related to the table T2. So what we can do is we can push down the predicate through the join. So basically, we want to evaluate the predicate first. That will reduce the input size of the join and speed up the join performance. For example, at the beginning, the join need to join 1 million records from T2, but after the optimization, it only need to join 1,000 records from T2. So this is called filter pushdown. And after this transformation, we find that only 2 columns are needed at last. From T1, we only need the column ID and value. From T2, we only need the column ID. So what we can do is to add 2 project nodes to explicitly select the 2 needed columns. So with this change, we are able to avoid shuffling unnecessary data. And because table T1 and T2 may contain hundreds or thousands columns, if the underlying table T1 and T2 is a database or a columnar format like Paquet or RC, and you can even push down the projection into the source to avoid reading unnecessary data and reduce a lot of I/O cost. And now we already get an optimized logic plan. At the last stage in the optimizer, we will convert the logic plan into a physical plan. A physical plan describes how to conduct the computation. For example, whether it is a broadcast hash join or a sort merge join. I will take batch as an example. So in batch, the join logical node will be converted into all possible physical nodes, including sort merge join, hash join, and broadcast hash join. But in this case, broadcast hash join will win because the size from table T2 is small enough. There is only 1,000 rows after filter. The cost of broadcast hash join will be the smallest. So in the final physical plan, optimizer will choose broadcast hash join as the physical node of the join. Of course, there will be some other rules involved in this stage. For example, merge project and filter into a calculated node. So a physical plan is the result of the optimizer. It's the final state of optimization. So after that, we will translate it into transformation trees, which with the code generation mechanism. For example, the calculated node which will filter out records whose ID is smaller than 1,000 and then select just the column ID. Flink will generate the executable Java code for this node. The generated code example is just shown at the right top side. And finally, the transformation tree will be compiled into a job graph and submit to the cluster for execution. So this is the whole lifetime of a Flink SQL program. In the above example, we talked about the physical planning for batch, but there are some special things for streaming. In the physical planning, the streaming need to do something special. The most important is the changelog mechanism, also known as the retraction mechanism. So you may have the question, what is changelog and why we need it? In order to answer this question, I would like to give you an example first. And this is a cascading aggregation. It first conducts a simple word count aggregation, and then calculates the frequency of each count. And if you have 3 words, 2 hello and 1 word, then the expected result should be like this. The frequency of count 1 should be 1, and the frequency of count 2 should also be 1. But in many streaming systems, there's no concept of changelog or retraction. Many systems regard the data flowing in the pipeline as independent records. that is problematic because it can't handle the cascading aggregation. In this case, by now we already received one hello and one word, so the frequency of count 1 is 2. Then another hello record comes in. The first aggregation will accumulate the hello count from 1 to 2, and emit the latest result, hello 2. When the hello 2 arrived to the second aggregation, it's a new record for count 2, so it will insert count 2 frequency 1 into the result table. However, the result is wrong, because now the hello has 2 records and word has 1 record, so the frequency of count 1 should be 1, not 2. So one of the most important contributions of Flink SQL is the changelog mechanism. With the changelog mechanism, every record has a meta to represent what's the change operation of this record. A change operation can be insert, update, and delete. Yes, they are also known as the SQL DML statements. And the source, for example, this source will emit 2 insertion records. And hello, they are hello and word. The first aggregation will accumulate them and emit 2 insertion records too. The first one is hello count 1, and the second one is hello count 1. So the frequency of count 1 is 2 now. Then another hello record comes in. The first aggregation will update the count of hello from 1 to 2. So this is an update operation. In many database binlog systems, they will check the update operation in 2 records. One update before and one update after to represent the before and after content of an updated row. So Flink also does like this. For example, we will generate an update before for the previous image hello 1 and an update after for the new image hello 2. When the updated before arrives the second aggregation, it will first do the retraction for this record to minus the frequency from 2 to 1, and then the update after will arrive the second aggregation. It will do the accumulation for this record. It will insert count 2, frequency 1 into the result table. So, as you can see, with the changelog mechanism, the final result is correct. The update before is the point of this problem. That's why we need the changelog mechanism. But not all the cases aggregation need to send update before messages. For example, if the downstream is an absurd sink which can replace radius by key, then we don't need to send update before messages to the sink to avoid some I/O costs. It can just take the update after and to replace the radius. And the query optimizer will help us to infer whether the update before is needed or not. And all the things happen in internal of Flink SQL. Users are not aware of it. So how the query optimizer invers the a node should generate update before or not, and whether a node will produce updates. The optimizer will analyze it in 2 steps. First, it will determine what changes will a node produce. There are 3 kinds of changes: insert, delete, and update. It is the same to the SQL DML statements. We do not care about how to encode update changes in this step. So we use I to represent insert, U represent update, and D represent delete in the figure. It is the same to so here is the so here is the physical plan of the count frequency job. And from the bottom to up, a source to scan the words table, and an aggregation to count the word, and a calculation to project only count field, and an aggregation to count the frequency, and then output it into Apache Flink. The source will produce insert only messages, so we tag I on this node. And then the word count aggregation will produce updated messages, so we tag I, U on this node. And the calculate will forward all the messages, so we also tag the I and the U on this node. And at the count frequency aggregation is the second aggregation, and it knows the input contains updates, so it will produce delete messages too. So we will tag IUD on this node. So this step is quite simple. In step 2, we will determine how to produce updates, either emit update changes with a row of update before and a row of update after together, or just a single row of update after. And we use the UB to represent the update before, and UA for update after. We will trigger the rule from the sync. For example, the Apache sync doesn't need the update before, so it tells in the input, please give me only update after messages. But before the aggregate answers the sync, it will require its inputs first. The aggregate knows the input contains some update changes, so the aggregate will require update before and update after together to make it can produce a correct result. The calculator will forward this requirement. So the first aggregate requires nothing because the input is a source and produce insert only messages. There is no updates in source. So the first aggregate will produce the before and after together because the downstream aggregate requires the before and after. And the calculator will forward it. And the second aggregator will produce only after because the sync requires only after. So tag the UA on this node. So we will get such a final physical plan for the streaming query. The tags will actually affect the behavior of the physical operators. For example, the frequencies aggregate knows the inputs contains updates, so it will use the count with rechecked implementation to handle the rechection logic. And it will not generate update before because it doesn't have the UB tag. And the word count aggregate will use a simple count implementation because the input doesn't contain updates. And it will generate update before because it has the UB tag. So this is a special story for streaming queries in the optimizer. Okay, let's talk about some major optimizations in Flink SQL. An universal performance improvement in the Flink SQL is the internal data structure. In the older planner, most widely used data structure is row. All the top-level records that are traveling through the Flink SQL pipeline during runtime are all row instances. And also many state structures are also using row. And look at this example. If we have a row consists of 3 fields, one is the integer and followed by 2 strings. It's actually backed by a very simple Java object array because we have to pay some cost on Java object headers or something else. Such a simple row will easily cost more than 100 bytes in JVM memory. So it's not efficient for space. Furthermore, we want to access some fields from it, but we have to pay the cost of boxing and unboxing. Last but not least, we actually faced a lot of serialization and deserialization when randomly accessing. You may have the question, why does the object array have to pay the cost? That's because if we want to transfer this object to network or save it into a checkpoint, it must be a binary format. And supposing we have a row with 200 fields, and you just want to access the 100th field and do some filter on it, you have to deserialize all the 200 fields, or at least the 100 fields. But actually, only one field is needed. All the others is a waste of resource. That's why we proposed the binary row as the basic data structure in Flink Planner to replace row. Binary row is integrated deeply with Flink's memory segment. I will briefly introduce the layout of binary row. Still the previous example, the layout is divided into 4 parts. The first one is the header part, which used to store a row kind, indicate whether it is an insert or delete or update change operation. We already introduced the change operation in the previous section about the changelog mechanism. And the second part is the fixed length part. Each field will have 8 bytes in this part. If the data is small enough to be stored in 8 bytes, for example, integer or long or double, then we can store the real data as it is in this slot. Otherwise, we will store the real data in a variable length part and store a pointer in the fixed length part, which points to the address in the variable length part. And yes, string is this case. So it's really an efficient and compact layout. And the biggest advantage of binary row is there is no need to deserialize the whole binary when shipping from network to operators, because the binary row is just a wrapper on the underlying bytes. You can randomly access fields, and deserialization can happen lazily. For example, if you want to access the 100th field, only the 100th field will be deserialized when accessing. You don't need to deserialize the 99 before fields. So we don't need to pay the cost for unnecessary deserialization. We also introduced other binary structures for the same purpose, including binary string, binary array, and binary map. We use them as the basic data structure in Flink Planner for both streaming and batch. It not only works perfectly in batch, but also improves a lot of performance in streaming. There is a very nice blog published in the Fabrica website, which tried a lot of benchmarks and explained in detail why the deserialization and serialization is the point that makes Flink Planner is more than 50% faster than the old planner. I put this blog link at the bottom of this page. If you are interested in it, you can read it after the talk. We also improved some operator implementations. One of them is the mini-batch processing for aggregations. Let's take a simple aggregation query as the example. In this case, we want to group by color and do a simple sum. If we take a look into the aggregation operator, you will see that for each record comes in, we will first look up the state to deserialize the previous sum accumulator from the state and do the aggregation. And then we may output some result and serialize the new accumulator back into the state. So typically, each incoming record will cost one state reading and writing, one serialization and deserialization, and one or two more outputs. So what we can improve in this case? The most performance critical factor of Flink streaming application is the state accessing. A lot of streaming optimization is around this point. So the mini-batch processing is the case. Instead of doing the calculation for each record, we will actually buffer the records into some heap memory to hold the bundle. There are two triggers to trigger the bundle calculation. One is the time limit, and the other is size limit. You can also use both of them. When the bundle is triggered, we will aggregate the buffered records into a single accumulator for each key, and merge this accumulator with the one in the state. So there is only one state accessing per key for so many buffered records. So you can get a very significant boost in throughput. And this also reduces the output amount and its downstream loads. Mid-batch processing can improve the throughput, but we still face a lot of aggregation school problem. School handling is a very common situation, which will happen not only in classical batch processing, but also in the streaming processing. It will happen in join or aggregation or other scenarios. Let's take aggregation as an example. So in this case, still the previous example. And for each key, we will key by the color to the downstream operators. And for the same key, the downstream operator will execute it in a single thread fashion. So it's very easy to be the bottleneck if the data is unevenly distributed. In this example, the red records is far more than the purple records. So the yellow aggregation node will be the bottleneck of this job. No matter how many resources you want to give to this job, the performance improvement will not be obvious. So we introduced some local aggregation chain after the map operator before shuffling. We call it the two-phase optimization. This is very like the MapReduce local combiner. So we can partially aggregate the data in the upstream operators. This can redistribute the computation evenly and reduce the amount of shuffling data. The data shuffling from the local aggregator to the global aggregator is actually the accumulators. So the global aggregation will not be the bottleneck anymore. It will receive very small and less more data. And you can turn on this optimization by the above configurations. And this is another interesting use case. You may know that it's impractical to do a general sort in streaming. A general sort means that the sort field is not an even time or processing time, but a regular field, maybe any type. A general sort requires that you have to wait all the data to arrive, but that's impossible for a monolith string. Or you have to image the whole sorted data set when you received each record. If you have received 1 million records, you have to output 1 million sorted data set for the new coming record, and then 1 million again for the next one. So it's quite expensive and unpractical. However, if users just care about the top N elements, then it will be possible. For example, if users want to calculate the top 3 shops by sales for each category, first of all, you can use such query with row number and a filter to do the top N. Such query is also widely used in other systems, for example, Hive and Spark. So there is no new syntax is proposed by Flink. In this query, we use an overwindow to calculate a row number for each record. The overwindow is partitioned by category and ordered by sales. So each category will have a ranking list, and the higher selling shops will have a higher ranking. And in the auto query, the filter will filter out all the shops with a row number larger than 3. In this way, we keep only the top 3 shops. So we will get such a original logic plan. In the original logic plan, we have to do the row number of aggregation first. But this is unpractical. But this is unpractical for streaming because it is similar to the general thought. So how to make it possible in streaming? The point is plan rewriting. We have an optimization rule to find the pattern that the low number of window is followed by a filter with a low number condition. Once such plan pattern is found, the optimization rule will convert the over window and the condition into a dedicated rank operator. The rank operator can be quite efficient, which can only store the top n elements in its state and use the heap sort algorithm to update the result. And in production, the rank operator can be as fast as a simple aggregation in some cases. Okay, at last, I will give a short summary and look into the futures. Actually, Flink already took a big step forward to the truly unified architecture. It's not just a concept or a slogan anymore. We always say that batch is a special case of streaming, and you can see that the unification really happens in the API and architecture and code. We introduced how Flink SQL works step by step, and we also look into the changelog story in it. And Flink SQL also does a lot of optimizations for users automatically. For example, the filter pushdown, projection pushdown, the binary row, and the aggregation school handling, and many more optimizations in the future. The most important is that users don't need to learn the optimizations. All the optimizations happens automatically. And all the existing SQL jobs can enjoy this all the optimizations. And a little about the futures. In 1.11, we will focus more on the feature and API development. In 1.11, first of all, the Blink Planner will be the default planner. That also means Blink Planner is ready for production. And we will have a new table source and table sink interfaces to make the connector more flexibility and support more advanced features like integrate with binary row and to support readings on change logs like the MySQL bin log. And furthermore, we will introduce a unified file system connector. No matter it is stored in the HDFS or S3 or Hive table, they can be used as batch table as well as a streaming table, and both support reading and writing. Besides, we would like to support a compatible mode for Hive DDL and DML, which means you can run Hive DML and Hive DDL statements and queries on the Flink SQL directly. That will be really awesome. So, thank you for the listening, and any questions?